In this module, we'll cover stimulus generalization as an extension from stimulus discrimination. To that end, how is stimulus discrimination defined? And what about stimulus generalization? Note that generalization is a result, not a behavior. Technically, we don't generalize as a behavior. We can't reinforce generalization. Generalization is something that happens given certain types of learning histories. So we want to figure out why and how that happens. Firstly, as considered during last module, what are the conditions necessary for stimuli to acquire control of a learner's behavior? This is a huge question, but in general, we have plenty of evidence now that reinforcement of behavior in the presence of given stimuli is likely to establish stimulus control. In the future, stimuli that have been present during reinforcement are likely to increase the probability of that response occurring again. So then, what are the effects of discrimination training on stimulus generalization? What learning histories will make generalization more or less likely? Iverson and Littell's text states that when an animal is trained in a stimulus control task, other stimuli not present during training may come to exert some degree of control of the animal's responding. But why? Saying that generalization occurs describes the phenomenon, but doesn't explain it. Well, as it turns out, it comes down to physical similarities between training and testing stimuli. This is a stimulus generalization gradient. Different stimuli are shown along the x-axis, and mean rates of responding in the presence of those stimuli is shown on the y-axis. In this case, wavelengths of light are the different stimuli. That means different colors. A 580 nanometer wavelength of light is orange. So, a pigeon was trained to peck in the presence of an orange stimulus, and stimulus control developed. Now we want to test whether the pigeon will peck in the presence of other colors. 590 nanometers is a kind of reddish orange. We see that the pigeon still pecked at a pretty high rate in the presence of that stimulus, but at a lower rate than when orange was presented. 600-ish nanometers is redder still, and occasioned a lower rate of pecking. The further we get to the right on the x-axis, the less orange the stimulus become, and the lower the rate of pecking occasioned by that stimulus. We see the same pattern on the left side of the graph. As we move right and the wavelength of nanometers increases, the stimulus becomes more red. So what color do you think it will become moving left? The further left we go, the more yellow it gets, and it actually carries on all the way through green. So, a generalization gradient shows that the more physically different a testing stimulus is from the training stimulus, the lower the probability of responding occasioned by that stimulus. Remember that these gradients show purely the effects of the antecedent testing stimuli. No reinforcement contingent on responding is delivered during testing. The stronger the stimulus control exerted by the training stimulus, the less stimulus generalization we'll see. The solid line on this graph shows generalization testing after non-differential training. In this case, the pigeon's behavior of pecking a light green stimulus was reinforced, but the behavior was never explicitly extinguished in the presence of any other stimuli. We can see that pecking was likely in the presence of that stimulus during testing, and gradually became less likely in the presence of other colored stimuli. During differential training, though, both an SD or S+ and S delta or S- were used. Responding was reinforced in the presence of a light green stimulus, and when an orange stimulus was presented, responding was extinguished. Interestingly, the stimulus a little quote-unquote more green than the training stimulus actually occasioned slightly higher rates of responding than the training stimulus itself, because it was even more physically different from the S delta. We then see the rest of the stimulus generalization gradient. It's much more steep than the other gradient. A steeper peak means that there is less stimulus generalization, which in turn means more stimulus control exerted by the original training stimulus. A flatter peak, again shown here with the non-differential training data series, means that there was more stimulus generalization. Assessing stimulus generalization can give you information about what parts of the training stimuli are actually controlling the learners responding. From Iverson and Littell's text, selective control by one dimension of a stimulus can be referred to as an example of determining what a learner is quote-unquote paying attention to. If I reinforced responding in the presence of the white triangle on a black background at the top, and extinguished responding in the presence of the white plus sign, what testing stimuli would end up occasioning responding during testing? If I responded during testing in the presence of the black checkmark in set 18, but not in the presence of the black triangle in set 18, what seems to have stimulus control over my behavior? What if I responded in the presence of the number sign in set 27, but not in the presence of the plus sign pattern in set 24? These stimuli are a little harder to lay out on a generalization gradient x-axis ahead of time, since they're not on a continuous spectrum like wavelengths of light. But based on the rates of responding we see in the presence of each during testing, we can create one. Let's say the training stimulus was the white plus sign on the black background. Maybe the generalization gradient would look a bit like this, with the stimulus becoming more different on the black background on the right, and the background becoming lighter and more complex on the left. In an experiment with these stimuli, rats were trained to jump toward the triangle, and jumping toward the plus sign was extinguished. These stimuli were presented simultaneously, and the side on which they were presented was alternated across trials. What type of schedule would that be? Then, the rats were presented with the other pairs of stimuli shown here, again presented simultaneously and on alternating sides. The rats did not reliably jump toward the triangle-like stimuli in the pairs marked in red here. Responding was at chance levels divided between the two options across trials. However, the rats did jump toward the triangle-like stimuli in the other sets. So what was controlling their behavior? The authors of this study reported that training the rats with a single pair of stimuli resulted in the animals placing the test figures into two categories, although we don't know the defining characteristics of the categories. We can't say what the rats were thinking. That would be mentalistic and not parsimonious. But we do know the effects on their behavior, so it would be possible to further investigate. Let's make this a bit more applied. Let's say you wanted a client to say orange in the presence of pictures of oranges and actual oranges, but not in the presence of other fruits. What stimuli should you use during discrimination training? If we only train in the presence of one stimulus, we can't be sure what precise stimulus control and stimulus generalization will develop. Will responding be occasioned in the presence of a whole orange or a different kind of slice? What about in the presence of an apple or a slice of apple? We do want the former to occur, but not the latter. So how can we increase the likelihood of that? We need multiple examples and non-examples. In a traditional discrete trial training format, we'd present one non-example at a time, accompanied by two or more non-examples. At least two non-examples are ideal, so that there isn't just a 50-50 chance of the learner responding correctly. We would want to have many examples, always including the critical variables of the concept of an orange, but changing across variable attributes such as size, color, shape, etc. We'd then also want many non-examples, both close in, that is quite similar to the example, and farther out, that is more different than the example. And again, since it's ideal to include two non-examples in the presence of each example during training, we'd want another set of non-examples as well. Since this allows for differential establishment of stimulus control, we're likely to see less inappropriate stimulus generalization while still encouraging stimulus generalization within the stimulus class of oranges. Here's another real-world example. Based on your learning history, what would you say in the presence of the middle stimulus circled here? What about the one on the right? And the left? Some people, maybe you as well, would probably just say purple in the presence of each of these. But let's say that a specific response was reinforced in the presence of the middle stimulus and extinguished in the presence of others. At that point, we'd see a steeper generalization gradient develop. These colors all have different names, and that's important to some people. They need to develop strict stimulus control by each slightly different color and prevent overgeneralization across shades. When working with any kind of client, think about what should be controlling their behavior long-term in the real world, and be sure to develop stimulus discrimination training procedures that will be more likely to lead to appropriate stimulus generalization without overgeneralization.